Welcome to Statistical Sampling 3B, a technical side note on how to generate distribution functions. In the series Tutorial 3, we look at developing intuition through simulation. In 3A, I showed you the distribution of the sample mean from an overall population distribution. In this technical note, I'll show you how to generate this population distribution. You can easily skip this tutorial if you're just interested in sampling. However, if you want to play around with crystal ball yourself to develop more intuition about sampling on your own, which I strongly encourage, then you may want to watch this tutorial. Recall that the population distribution in tutorial 3A looked something like this. If you are interested in how I generated this distribution, here is what I did. I start with the distribution gallery that crystal ball offers us. I thought a normal distribution should somehow impact our population distribution. I thought a triangular distribution seems to be easy to work with. I know that a beta distribution can assume almost any kind of shape you want to give it. And finally, I wanted to have something that is right extreme, so the minimum extreme function with its mode height towards the right hand side looked good to me. Now I need a strategy on how to generate the population distribution. Overall, I would like most values to be between 0 and 400, and I would like the mean mu to be 200 and the standard deviation sigma to be 100. There's nothing particular magical about these numbers, but it's easy to work with. Next, I decided that I would like the triangle distribution to dominate the left-hand side of population distribution and peak at around 100. The normal distribution I would like to peak at 200, the minimum extreme distribution around 300, and the beta distribution around 350. Again, there's nothing magical here. This is just for me to get started. In crystal ball, I enter for the triangle distribution a minimum of 80, a likeliest of 85, a maximum of 150. This looks like this. Remember that whenever you enter data into crystal ball, you never enter the data, you always refer to a spreadsheet cell with those values. On our range from -50 to 450, this looks like this. Notice that a triangular distribution with these parameters has a mean of 105 and a standard deviation of 15.94. For the normal distribution, I chose a mean 200, and I will tell you later how I determined the standard deviation. The minimum extreme distribution, the likeliest value is 300, so our minimum extreme distribution will peak at 300. And the scale factor, which basically determines the size of the variance, I arbitrarily set to 60 because I like this particular shape. This yields a mean of 265.37 and a standard deviation of roughly 77. Finally, for the beta distribution, I chose a minimum of 220, a maximum of 350, and by choosing alpha to be 5 and beta to be 1, the beta distribution assumes this shape, which is strongly skewed to the right. The mean is 328.33 and the standard deviation about 18.3. On our entire range from -50 to 450, the beta distribution looks like this, such that overall the following situation arises. The question now is, how much weight should I assign to these distributions? I arbitrarily decided to assign 30% of weight to the minimum extreme distribution, so 30% of all my values will be determined from this one, 15% to the beta distributions, and now the question is, how much do I assign to the remaining two? It turns out I don't have any freedom of choice here anymore for the last two distributions, because the overall mean of the entire population will be just the weighted average of the means of the individual populations. Since I want that to be 200, I need to have R1, the weight I assigned to distribution 1, the triangle distribution, times 105, plus R2 times 200, plus R3 times 265, plus R4 times 328, must equal to 200. As I have assigned R3 to be 0.3 and R4 to be 0.15, I can only choose between R1 and R2, but R1 plus R2 now has to equal to 0.55. Two linear equations, two unknowns, means I have exactly one solution, and I assign about 41% of the weights to the triangle distribution and 14% to the normal distribution. If you are watching this technical tutorial, you are the type that would actually like to figure out how to determine the variance. So here we go. But be warned, this is going to be some mathematics. However, in the end, I think you can follow and it will be kind of fun. Recall that we wanted the standard deviation of the population to be 100. Now here's the general formula for determining the variance. Since the standard deviation has to be 100, we want the variance to be 100 squared, or 10,000. So let's see if we can work with that. Well, what is fx? The PDF of our overall population. Well, the PDF of our overall population is simply the weighted average of our 4 individual PDFs. That from the triangle distribution, the normal distribution, the minimum extreme distribution, and the beta distribution. So let's substitute that into our formula for the variance. Now, we can also, because the functions here are well behaved, nothing crazy is going on, exchange the summation with the integration sign. Thus, let's focus on simply the integration for one of the 4 distributions. And let's see what we can do here. Let's introduce the distance between the global mean mu and the local mean of distribution I, mu sub I, as delta sub I. Then, for minus mu, we can write minus mu sub I minus delta sub I. And let's substitute that into our integral and take the constant r sub I to the outside. Now, let's multiply out the square, at least partially, which then looks like this. Splitting the integral up into 3 yields this expression, and taking the constants out in front of the integrals yields, what is this integral? Think about it for a few seconds, or stop the tutorial here and think about if you have seen this expression before. What does it mean? Well, did you have some time to think? Here it is. It is simply the definition of the variance of distribution I, which we denote as sigma sub I squared. So let's take that out and substitute sigma sub I squared. Let's look at the next integral. Again, you may want to pause the tutorial here and think about what this means. I'm sure you have seen this before. I hope you spent some time thinking. Here's the answer. It is the definition of the mean of distribution I, so simply mu sub I. Let's substitute that. And finally, let's look at the last integral. Now this one you definitely should know. Give yourself some time to think about it. What is this? It's simply the total probabilities of distribution I, which is simply 1. So this cancelled out. What we are left with is remarkably easy. And notice it gets even easier because 2 more terms cancel out because they're identical, leaving simply for our solution r sub I times sigma sub I squared plus delta sub I squared. Recall that this is the solution to the integral on the left-hand side. To interpret that, let us resubstitute for delta sub I mu, the global mean, minus mu sub I, the mean of the distribution I. In a sense, the left-hand side tells us the contribution of distribution I to the total variance of the population sigma squared. And it is simply the squared distance of the global to local mean plus the variance of distribution I multiplied by the relative weight of distribution I. That makes actually sense. Distribution I contributes in two ways. In one way, by its own variance, and in the other way of how far it is away from the global mean. And it turns out that we simply add those two up, or the squares, and multiply it by the relative weight. So recall that this expression was part of a larger expression to determine the overall variance of our population distribution. Now let's substitute the right-hand side into this, and now we are able to calculate everything we want. Recall that I didn't determine the standard deviation for the normal distribution beforehand, because I want to give me some degrees of freedom here to make sure that the standard deviation of the total population will be 100. Well, that means the variance, sigma square, has to be 10,000, and that means the right-hand side column has to add up to 10,000, which in turn means the right-hand side value for the normal distribution will be determined to be 625.92, and given that, I can simply determine the standard deviation sigma sub I to be 66.6, which in the end will mean that I have now overall population distribution with mean 200 and standard deviation 100. The rest now is smooth sailing. We have all our data in our Excel spreadsheet. We have defined the assumption cells, and now I add a fifth distribution, a simple uniform distribution between 0 and 1. Basically, the value from that distribution will decide which of the four distribution values we will take. Let me explain how this works. Let's simply step into the simulation. The random number we first obtain is 0.75. Now, 0.75 is between 0.55 and 0.85. That means we will take the value from the minimum extreme distribution, 284.06. Let's try this again. The next random number is between 0 and 0.41. That means we'll take the value from the triangle distribution, and so on. All that remains now is to copy the whole thing 36 times, and now we have observations from 1 to 36, or however many we want, and we are done. I'm looking forward to seeing you in the next tutorial, where we will discuss the important difference between the sample standard deviation S and the population standard deviation sigma. See you then.